Hello everyone, this is our session 2 on linear programming. Okay, so we are going to start with linear programming problems now. So what is this linear programming problem? We have studied linear equations and inequations in this chapter. We also learned how to find the graphical solution. The word programming means planning and refers to the method of determining a plan of action for the optimum use of available resources. Basically, we can talk about mathematical problems in manufacturing units, in you can say transportation units. So they are having constraints, right? Now, what are these constraints? So we have manpower. Manpower works for a particular amount of hours, but they have targets to complete. What are these targets? So let us say that we have a bicycle manufacturing company. So it has a target of completing, let's say, 100 bicycles by the end of a month. And they have just say 5 laborers a day working for 8 hours every day. So they may include the weekends, which is an off for them, or maybe one of the days of the week is an off. So will they be able to complete it in that much amount of time? That's how we optimize the solution. We get in more manpower, we increase their working hours, or we check for if we could get an extended time for the 100 bicycles. So that's how we work on linear programming problems. Okay, so basically we have some constraints, then we have an objective, and we have to optimize the objective by using our constraints. Okay, so let us begin with an example. Okay, now I'm going to read out the example and make a table according to that. Uh, Let me just share the screen. Yes. So a manufacturer produces bicycles and tricycles, each of which must be processed through two machines, A and B. Okay, so what we'll do is very important thing in linear programming is the table. Okay, the table does most of your work, so you should be very clear with the table. Okay, first of all, understand what all we put inside the table. So first, it must be processed through two machines, A and B. So we'll put the machines over here first. Okay, machines say A and B. Okay. Now, time required per unit. That is, what do we have? We have bicycles, right? And we have tricycles. Okay. So what we can do is we can write over here time required per unit. Okay. So per unit. Okay, that's little small table. 1 minute. Okay, so now we have the table here. A manufacturer produces bicycles and tricycles, each of which must be processed through two machines, A and B. Machine A has a maximum of 120 hours available. So maximum time it has is 120. Okay, and machine B has a maximum of 180 hours available. Okay. Manufacturing a tricycle requires 6 hours on machine A. So let's say on machine A, it requires 6 hours and 3 hours on machine B for a tricycle. Okay. Manufacturing a bicycle requires 4 hours on machine A and requires 10 hours on machine B. Okay. If profits are rupees 45 for a tricycle and rupees 65 for a bicycle, formulate LPP to have maximum profit. Okay, now you have to understand what is maximum profit. So maximum profit, let's say I have X number of cycles and Y number of tricycles. Okay, Then per bicycle, I am going to get rupees 65. Okay, and per tricycle, I am going to get rupees 35 as a profit. So if let's say I manufacture X bicycles and Y tricycles, okay, then what will be my profit? So it would be 65x plus 35y. Okay, I'll call this function as Z. Okay, so Z is equal to 65x plus 45, sorry. So per tricycle, it is 45. Okay, 65x plus 45y. Then the total profit to the manufacturer is Z equal to 65x plus 45y. Okay, this is a linear function which is to be maximized. Hence, it is the objective function. Means this is my main aim, to maximize my profit. Okay, now since the number of bicycles and tricycles cannot be negative, so we always will have values of x greater than 0 and y also greater than 0. Okay, now since one bicycle requires 4 hours of machine A, so x bicycles will require 4x hours on machine A. Okay, so 4x hours on A. We are talking about bicycles right now. Okay, and Y tricycles require 6y hours on machine B. Now, if one tricycle requires, look at tricycle, it requires 6 hours on machine A, and bicycle requires 4 hours on machine A, then on machine A, how much work is done? So, one bicycle 4 hours, one tricycle 6 hours. X bicycles 4x hours and Y tricycle 6y hours. So, 6y hours on A. This you can say for bicycle and for tricycle, correct? So machine A basically will work for 4x plus 6y hours, okay? It will work for 4x plus 6y, but how much time do I have on the machine A? I just have 120 hours, so they can either work for 120 hours together or less than 120 hours. Similarly, we can do for machine B. So now look at machine B. It gives how many hours to the bicycle? 10 hours. So 10x hours would be for X bicycles and 3 hours for the tricycle. So 3y hours would be for the tricycle. So 10x plus 3y. Okay. 10x plus 3y. Now, how much time do I have on the machine B? Total time 180 hours. So this would be less than equal to 180. Okay. Now I'm going to put all the equations that we made together. Okay, and explain them in one go. So we have Z equal to 45 45y plus 65x. Okay. Now, the mathematical formulation of the given problem is maximizing Z equal to 45y plus 65x subject to the condition or constraints. Now, what are these constraints? So the first constraint is that the machine A can work less than equal to 120 hours, machine B less than equal to 180 hours. X value should be greater than 0, Y value should be greater than 0. Expression 1 is called objective function. This is your objective function. Expression 2 and 3 are called constraints. Okay, so this is 2 and 3. These are your constraints. Okay. Then what is x greater than equal to 0 and y greater than equal to 0? They are called non-negativity restrictions. Okay, so basically when we are talking about manufacturing, they are always positive solutions. So non-negativity restrictions have to be included in your LPP. Okay, so we have objective function, we have constraints, non-negativity restrictions. Okay, now main thing about LPPs, LPP, if the restriction when expressed mathematically are in the form of linear and equations, the programming is called linear programming problem. The restrictions are called constraints. Okay, so I wrote over there, second and third are your constraints. Objective function is what you have to maximize or minimize. You have to maximize profit. Sometimes you can have minimized the loss. Okay, so maximum or optimum value has to be found out. It's called objective function. Okay, what are the problems that you could get in this? Manufacturing problems, like we did just now, diet problem, transportation problem, problem related to investment, problem in the advertising form. Okay. Now, mathematical LPP formulations, what do we have to remember? Identify the aim, the objective of the question, okay, and you equate it as Z or you denote it as Z. Identify the variables and assign symbols X, Y, or how many ever variables are available, or you can say X1, X2, X3 as well. Identify all the restrictions or constraints in the problem and express them as linear inequalities or linear inequations in terms of variables. Express the hidden condition generally involve non-negativity of variables. Hidden conditions is this exactly what they're talking about. And don't worry, in this chapter, you're only doing non-negative constraints and we are going to do only two variables. So no more than two variables you have to work with and non-negative constraints are there. So no hidden other conditions would be given to you. Okay, I'm beginning with exercise 7.3 doing question 1. A manufacturing firm produces two types of gadgets A and B, which are first processed in the foundry and then sent to a machine shop for finishing. So we are going to make a table. Okay, exercise 7.3, first one. Let's make the table. Okay. So we have two gadgets over here. So we have gadgets A and B. Okay. We have foundry and we have machine shop. Okay. Now, a manufacturing firm produces two types of gadgets, A and B, which are first processed in the foundry and then sent to a machine shop for finishing. The number of man-hours of labor required in each shop for production of A and B, and the number of man-hours available for the firm are all as follows. So, in the foundry, gadget A requires 10 hours and gadget B requires 6 hours. The total availability of the foundry, okay? So, time available we'll put over here. Time available is how much? So it's 60 hours for the foundry, okay? And machine shop, we have 5 hours for the gadget A and 4 hours for the gadget B, and total hours in the machine we have 35. Okay. Profit on the sale of A is rupees 30 and B is rupees 20. Okay. So rupees 30 profit for A and rupees 20 profit for B. This is given to you as a sum. Okay, now how do you proceed by it? So, see, this table is already mentioned. You have to make your own table wherein you can put the variables, you can put the constraints. Okay, so first of all, we can say let the number of gadgets, you can say the number of A gadgets, you can say is X. Okay, is X and number of B gadgets would be Y. Okay. Equal to Y. So how much profit could it make? So 30x plus 20y, okay, equal to Z. This is your objective function. Okay, this is a linear function which is to be maximized, hence it's the objective function. Now let us put the table. So now we'll make our table, the solution table, Okay, now in the solution table, what would we have? Okay, so let's say we'll have the foundry and the machine shop. Okay, so we'll have gadget A, we'll have gadget B, and we'll have the total time. Okay, so we have X, Y, okay, and time. And we have over here the foundry and the machine shop. Okay, so the gadget A takes 10 hours in the foundry and it takes 5 hours in the machine shop. Okay, gadget B takes 6 hours in the foundry and 4 hours in the machine shop. Total hours of the foundry that are available are 60 and total hours of the machine shop are 35. Okay, so the equations that constraints we'll have is, see, the foundry is giving you 60 hours. In those 60 hours, X will also be working, Y will also be working. But how many? So we'll say 10X plus 6Y, okay, should complete their work in less than equal to 60 hours. Okay, yeah. And the second constraint now would be 5x plus 4y. So in the machine, x is taking 5 hours and y is taking 4 hours. They have the availability of only 35 hours. So these are your constraints. Okay, and it's a non-negative function, so we have to write this as x greater than equal to 0 and y greater than equal to 0. Okay, so we have four equations here. First is your maximizing function objective, 30x plus 2y, 30x plus 20y is equal to z. Okay, and subject to, or the constraints are, 10x plus 6y should be less than equal to 60, 5x plus 4y should be less than equal to 35, and x greater than equal to 0, y greater than equal to 0. Okay, that is question 1. Okay, now let us move to question number 2. In a cattle breeding farm, it is prescribed that the food ration for one animal must contain 14.22 and 1 unit of nutrients. Contain 14, 22 and 1 units of nutrition A, B and C respectively. Two different kinds of fodders are available. Each unit of these two contain the following amount of these three nutrients. Okay, the cost of the fodder is 1 rupee per, fodder 1 is rupees 3 per unit and that of fodder 2 is rupees 2. Formulate the LPP to minimize the cost. Okay, now there is a minimizing function, so your objective should be minimizing objective. Okay, now what I'll do is first I will write down the sum that they have given us. So we'll make a table of the sum that is available. Okay, so we have, what they have given us is this. Okay, so fodder, two types of fodders are there basically, so 1 and 2. Okay, and we have nutrients. Which are these nutrients? So A, B and C. Okay, now there are 2 units of nutrient A, 2 of B and 1 of C in fodder 1, 1 unit of nutrient A, 3 of B and 1 of C in the fodder 2. The cost of fodder 1 is rupees 3 per unit. So fodder 1 is equal to rupees 3 per unit. Okay, and fodder 2 is equal to rupees 2 per unit. Okay, Now since you have cattle, so you have to have fodder as your x and y. So fodder 1 is x and fodder 2 is y. Okay, let x units of fodder 1 and y units of fodder 2 be prescribed. Okay, so you'll say let x equal to fodder 1 and y equal to fodder 2. Yes. Now we'll make our table. That is the table that we require to make an LPP. Okay, so what should be there in this table? What is the difference? I'll show you. So again, we'll have nutrient and fodder. That is correct. Okay. One second. This is fodder, nutrient. Okay. Then we have A, B, C here. We have fodder 1, fodder 2, and minimum requirements. That is, each vitamin minimum requirement is given to you. Okay, so 221 of ABC is present in fodder 1, 131 of ABC is present in fodder 2. Nutrient A must contain 14 units of nutrient A, must contain 22 units of nutrient B, and 1 unit of nutrient C. Okay, so from the table, fodder contains 2x plus y units of nutrient A. Okay, so let's say that your 2x plus y units of nutrient A. Okay, so fodder 1, nutrient A is 2x. Okay, and fodder 2 is x, and the minimum requirement is 14. So it could be at least 14 or greater than 14. Okay, so 2x plus y greater than or equal to 14. What is the B? So B would be 2x plus 3y. Okay, 2x plus 3y units of B. Okay, what is the constraint over here? Minimum, how much should be present? 2x plus 3y should be greater than or equal to 22. And the last one, x plus y greater than or equal to 1. Okay, units of nutrient C. Therefore, the constraints are 2x plus y greater than equal to 14, 2x plus 3y greater than equal to 22, x plus y greater than equal to 1. Since number of units of x and y cannot be negative, we have x greater than equal to 0 and y greater than equal to 0, and your minimizing function z will be equal to 3x plus 2y. So basically you should be spending optimizely for getting your fodder, right? You cannot be wasting money on that. That's why z is equal to 3x plus 2y should be minimized. So you have to mention over here, minimize z under the constraints of the equations 2x plus y greater than equal to 14, 2x plus 3y greater than equal to 22, x plus y greater than equal to 1, x greater than equal to 0, and y greater than equal to 0. Okay, these are your non-negativity constraints, and the remaining are your required constraints. Clear? So shall we complete with the chapter LPP? Now all the other sums are of the similar manner, but if you have a doubt in the same, you can write to me. I'll send you the solution for the same. Thank you so much.